So here's where we left things yesterday. Yesterday I discussed, let's say, the main effective field theory to describe strong interactions in nuclei and the interactions between the constituents of nuclei, namely neutrons, protons, and their exchange particles, pions. And this effective field theory is called chiral effective field theory because it uses as explicit degrees of freedoms the nucleons and the pion as Goldstone boson of the chiral symmetry breaking. Then we discussed, this is actually not the right screen. Then we discussed spin-dependent Wimp nucleus interactions, and in particular focused on the important role of two-body currents, where the mediator that is responsible for spin-dependent interactions couples not just to a single nucleon, but to two nucleons, and that can either be two nucleons that interact at short distances or two nucleons that exchange a pion. And I just want to alert you that there are fits for all the structure factors needed for all isotopes from the lightest one we calculate up to xenon. In these papers, the experimental collaboration has been using is this one here. And there's an update which is a re-evaluation of the uncertainties in the low energy coefficients that enter the two-body currents and includes some further improvements in this paper here, which is actually a paper for coherent elastic neutrino nucleus scattering, but there are some spin-dependent bits there that are relevant for both cases. So there are some tabulated fits here and here as well. Okay, so today we want to cover something first, again, related to spin-dependent. This will be very short. Then we want to look at an extremely interesting detection channel, if it would be feasible, namely inelastic scattering, where a Wimp doesn't only produce a recoil of the nucleus, but leads to an excitation of the nucleus, a nuclear excitation. And this we explored in this paper here at the same time as the spin-dependent interactions. And then I will leave spin-dependent interactions and discuss what is maybe called spin-independent plus, but discuss anything that has a scaling with a number of nucleons in the nucleus. So we call this general coherent Wimp nucleus scattering. So this has your favorite spin-independent cross-section, but includes a lot of corrections, and we also connect it to other works in the literature. And there are basically these two papers here. The most recent one is the one that's most up to date. And then I'll apply this both to two cases. One, we will look at how easy it is to distinguish these different coherent responses. And then we will discuss also briefly that one of these responses is the Wimp's coupling to the pion. This is less important than the standard spin-independent response, but stronger than the spin-dependent response. And there were some first limits for Wimp-pion interactions reported in a PRL of the xenon collaboration 2 years ago. So let us start with Wimp inelastic scattering. I will also try to stick to time, so I have much less slides than yesterday. So let's go back to the non-zero spin, namely the odd xenon isotope, which have non-zero spin ground state, so they interact by spin-dependent interactions. And let's look at the experimental, focus here on the experimental spectra. The ground state is here aligned to 0. And here's the spectrum for xenon 131. And you will notice the energy scale here is, I actually should have put some scales here, I'm sorry. This is the excitation energy in keV, kilo electron volt. And you see that the two unpaired species have low excitation energies, 40 keV for xenon 129 and about twice as high 80 keV for xenon 131. And these are very low excitation energies, so that from a nuclear physics perspective, if you have a heavy particle that hits the nucleus, it doesn't only have to scatter, it may be that it not only scatters elastically, but it could, in the scattering process, excite the nucleus to its excited state. Okay, and this is what we looked at in terms of inelastic Wimp scattering, where the inelastic is not referred to some dark matter model, or it's referred to the inelastic, that the scattering process is an inelastic process that takes the nucleus from the ground state to the excited state, here from the ground state to the somewhat higher excited state. And what you can see here are the calculations for the spin dependent. These are all spin dependent responses.
I don't think we could see the writing.
You can't see the writing?
You just, oh, sorry, I couldn't see it. Everyone else
Can
probably
you see
could.
it now?
Yes, I saw it on the side, on the very side. Apologies.
Okay. Okay, I will make sure to draw it closer. And so here are the spin-dependent structure factors or nuclear response functions for xenon 129, this guy with 40 keV and the one with 80 keV. And you can see the calculations both with two-body currents for the elastic channel. These are the hatched lines or the lighter lines, lighter bands, which are the ones we discussed yesterday, dominated by neutrons, and here dominated by neutrons. And then you can see it for inelastic scattering. At low momentum transfer, P is the momentum transfer. So for momentum transfer P 0, U is equal to 0. Of course, the inelastic excitation is very much suppressed. Then if you have more momentum transfer available, then you start to inelastically excite it, and then you go down because you don't have that inelastic excitation. So you can see here the bump from the inelastic excitation, and you can see that at this variable u around 1 or so, that corresponds to a momentum transfer of 150 MeV, the inelastic excitation is actually comparable to the elastic scattering. Now, in the experiment, you're mainly sensitive to this part here, but if you had some nucleus or some target or some experiment where you start to become sensitive to this inelastic increase, it's very interesting for the following reason. If you now look at the inelastic detection signature for an inelastic Wimp scattering, you would see this elastic recoil because the nucleus still moves. And there would be a gamma D excitation from the nuclear excited state, a 40 keV gamma for the xenon 129 and an 80 keV gamma from the xenon 131, which is of course also deposited as energy in the detector. Okay, and you can see here the recoil spectrum as a function of visible energy, and you can see that at low energies, it's dominated here by the elastic responses. So that is orange, cyan, purple, this bunch of elastic, individual and total, just as before. But then these bumps come in and you get basically shoulders from every inelastic excitation. And the first shoulder you get is from the nucleus, which has the lightest, smallest excitation energy, 40 keV, xenon 129 here. And at higher energies, you're also able to see the xenon 131 inelastic excitation with this shoulder. Okay, so this is very interesting because now the recoil spectrum is not just like for the total elastic, maybe I should make it with a color, total elastic here, which is this falling off recoil spectrum. But now you get from the total, which is with inelastic, these two shoulders, because the detector sees these two inelastic excitations. Okay, this particular plot here is actually for a Wimp mass of a 100 GeV. And if you just look at the kinematics, then you will see that for this kinematics, 100 GeV WIMPs, and for this mass, you're able to excite both of these. Here are the thresholds where these become accessible. So you'll be able to access both both the 40 and 80 keV excited state. But if the WIMP mass decreases, then there's some threshold where you only see, for example, for 25 GeV WIMP, you're in the only able to get the 40 keV excitation. And if the WIMP mass is even lower, then it would be a pure elastic signal. And for heavier WIMPs, of course, you can bump the nucleus more. Okay. So basically, if you could combine the information from these shoulders, relative information from these shoulders, you are accessible to the mass of the dark matter particle. And also because this signal looks different for a spin-independent and spin-dependent scattering, you would also know something about the dominant interaction channel, because in the case of, this is for spin-dependent, where you basically have an order 1 beginning here, structure factor. But if you would have spin-independent scattering, the beginning would be enhanced by a squared, and these shoulders come very, very late. So in principle, with some ideal detector that can see inelastic excitations in a single experiment, you're sensitive to mass. If you have multiple or even one excited state, and you're sensitive to spin independent and spin dependent. Okay, so it's a very interesting way of using a nucleus. Okay, now as you can see from the numbers here, of course, where you are compared to the low energy rate, then you're here sort of an order of magnitude weaker by coming to the first shoulder. So you can see that this is much more challenging, of course, than the elastic detection. Okay, with this, we can check off the inelastic scattering and come to the main part of today, which is to look at
May I ask a question?
Sure.
Sorry, I have to interrupt. I can raise my hand, but I'm the chair, so I can only say that I raised my hand. So I understand xenon is a very big nucleus and it has many isotopes. So I guess it favors the chances that you have these low-lying nuclear levels. Can you put this into perspective with other detector materials? I mean, I suppose argon is much lighter, so it probably is not awarded these low-lying states. Or would it be possible to build, say, a dedicated detector out of a material, out of an isotope with particularly low-lying levels?
Yeah, so it's correct. Actually, the better plot here is that for heavy nucleus, you have these, for odd mass isotopes, these low-lying excited states. I think another one that has a very low-lying excited state is germanium. And the lighter ones like argon also, of course, don't. But the only one that immediately comes to mind is germanium. So I can take that as a homework problem for myself and look it up and tell you in the exercise session.
It's only 3,000 or so nuclei.
Yes, so I know which paper to look at. Okay. Any other questions?
Yes, we have 2 raised hands.
Very good.
I don't know the order, but Michelangelo, Schreiner, please go ahead.
Yeah, I wanted, on the same line, I wanted to know if, like specifically for silicon, it would be possible to excite any states with low mass WIMPs.
I don't think so.
A theorist would say, you can use boosted dark matter. So you need to have, give dark matter a little bit of a velocity to favor kinematics of upscattering, of exciting a nucleus.
So, okay, I can just, if we look at this paper here, and this has all the spectra for what we thought are all Wimp relevant detection materials. So I can just go through the plots and tell you what they look like. So xenon you have seen. So you should be seeing this now. Iodine has a 50 kV excited state. Germanium has a very low lying excited state. That's why I remember germanium. Then these are fluorine and sodium. Notice that the energy changed here. So this is a couple hundred kV and 500 kV excited state. Aluminum almost 1 MeV. Silicon 1.3 MeV. And I think we're through the plots. Yes. So the interesting ones are of this collection here are germanium and iodine, with germanium being the lowest excited state and iodine, look back here, being sort of more similar like xenon 131, not quite as low as 40 kV. It looks like 70 or so.
Okay, we have also Gaurav, and then another question from Hefi. Hefi, I think, is order 8 people, so Gaurav, go ahead.
Yeah, thank you. Is it possible from this inelastic scattering to tell about the dark matter spin? Is it possible? Because it
to tell about
spin of the dark matter, because it could depend upon the excitation, which level it is excited. Is it possible to have that information? Yeah.
So yes, so then now we're asking very detailed questions, and I would have to look it up, but it's true that, of course, depending on what kind of probe you have, there may be some probes that don't enable such an excitation from 1/2 plus to 3/2 plus, or same parity. Here it's the other way around, and in the other nuclei the spins were different. Yes, so we would have to look at it and see for which type of dark matter particle and which exchange probe, scalar, vector, axial vector, and so on type of interaction we could get such an excitation.
I see. Okay, thank you.
One more question by Hefi.
Yes, yeah, this is Alexander from Hefi. I was wondering from an experimentalist point of view, because we're showing this plot of the rate in the shoulders and so on, and it looked like you would get probably a rate of 10 to the -5 kilogram days, so you would need probably a ton scale or higher than mass detector and years of exposure to get something in those shoulders. What kind of experiment would you propose to study this in terms of, I mean, we frequently have ton scale detectors already, but is this possible with other materials?
So in our paper back then, we concluded that we have some statements on this, which I would have to look up. But of course, it's very challenging, as you recognize from the rates. So I'm not, there are better people to answer this question than me. So I understand it's very challenging. Maybe Aina wants to comment to this.
No, it was maybe a slightly related question, but I was just wondering about iodine, whether you know if these prompt gamma D excitations would be visible in, for instance, sodium iodine scintillation crystals.
No, I'm sorry. I refer to the experimentalists for this one. I don't know. So I'm not a detector expert, and thank you. There are many people on here who know this better than a theorist like me. Sorry, I can't answer that.
Okay, there's still a raised hand by Hefi. Do you have another question, or this is the previous one?
Sorry, that was just.
Okay.
Where is Hefi?
It's the Institute of High Energy Physics. We are the main organizer.
I see. That's in Vienna. You actually could have a beer in Vienna. Okay.
Maybe they are. We don't know.
Yeah, they may be right now. Yes. Okay. So let's check this off. I find this also from the point of view of using nuclei and the aspects of nuclei as a material really interesting. I found this a great project, even though it's experimentally maybe it is extremely challenging. So let's now come to the general coherent Wimp nucleus scattering part. And I first want to go back to, we discussed yesterday that there's a systematic chiral EFT expansion where for nuclear forces at leading order, there were two-body currents. At the next order, there were corrections to two-body currents. And we assigned a counting in powers of Q to this. So leading order Q was 0. Next to leading order happened to be Q squared. And I took from a paper that we did a few years ago, an overview here of all possible Wimp nucleon interactions and order where this is arranged or where the table gives the chiral counting Q to the nu. Okay, so nu is equal to 0 would be the leading order stuff in two-body forces and so on. So we can check what we were just doing, which was the spin-independent channel. Here, let me circle this in orange. Spin-independent interactions. Actually, circle it in blue is better. These are, for example, here in the axial vector. What we discussed was in the axial vector channel. So here, and you saw that the leading response was two-body currents, and the one-body currents, was one-body currents. So that was this one here. 0 was the one-body current, and the two-body currents we discussed were these guys here, the leading two-body currents, which are Q cubed. So this is Q to the 0, and this is Q cubed. And they were from these type of diagrams that we discussed yesterday. Okay, and so in this table, this nicely organizes the leading one-body current order, nu is equal to 0, and the leading two-body current order, in this case, this row, Q cubed. Okay, so you can see that was what we discussed. This usual spin-independent case, for example, is scalar. So in this case, the one-body response is Q squared. Q squared. In this case, Q squared is actually a constant, not momentum suppressed, but in pi squared. And the corrections, two-body current corrections are Q cubed. And then you can see that there are even interesting channels. If the Wimp would be a vector current that talks to an axial current in the nucleon at the nucleon level, so a current interaction that is V to A, then you can see that in the currents, the one-body current is order Q squared and the two-body current is order Q squared as well. So there are some exotic channels, Wimp nucleon channel interactions, vector Wimp, axial vector nucleon, where the two-body current is as important as the one-body current. Okay. In addition, we did in this paper here a matching to what is known as a non-relativistic effective field theory. This is basically an effective field theory where you treat the pions as infinitely heavy. So we can also call it pionless effective field theory. The authors Fitzpatrick et al. Coined it non-relativistic effective field theory. So it only has nucleons, no pions, and therefore also none of the chiral physics. And they wrote down at this level 11 possible operators, where now you see there are no pions anymore. It's just short-range operators, 1 spins for the nucleons or momentum suppressed responses. Okay, and this analysis here also showed that these are things that I will also give you later in an overview, that these non-relativistic EFT operators, these 11 operators, if you include chiral physics, namely the specific aspect of QCD and pions, that these NR-EFT operators are not linearly independent. For example, operators 4 and 6, we will also see that later, both are part of the spin-dependent response. And so the coupling of an axial vector probe to a nucleus where there's nucleons and pions will be a combination of O4 and O6 and not separately. That was one point. And the other point that we observed is that if you look at all possible operators that exist, for example, up to power nu equals 3, so q to the power 3, and you can see there's many of them, then in fact there are only 8 of these operators present, not all 11. So chiral effective field theory, chiral physics, the pion physics implies some redundancies of operators or some linear dependencies of operators. QCD implies some dependencies of these operators and also arranges the relative importance of these 11 operators according to the chiral EFT counting. So let's discuss a little bit more. This was just at the level of the interactions. How we would set up a general coherent spin-independent Wimp nucleus scattering. And I want to use the iPad slightly here and then show you some results. So
may I just come back to your previous slide just for 1 second, because I think half the world is using now this non-relativistic or pionless EFT to sort of make the quote-unquote model independent analysis just by going through all these operators. So what is the real difference? The real difference comes in the Q-squared dependence, because these operators still carry a nuclear form factor and they will be different from the pion full theory, or what is, yeah.
Yeah, there are no pions in the non-relativistic EFT at all. All the pion propagators where there's lots of Q's in there, and also the pion couples derivatively Q dot sigma to the nucleon, all of this is switched off in the effective field theory, and it's unrelated. So you can see that here O4 is like a direct coupling to the spin, but O6 is a coupling to the spin of the nucleon, and O6 is a coupling where the spin and Q are dotted into each other. Resembles very much the way a pion couples to the nucleon. And so the fact that you have pions in the nucleus, and that the response is to a nucleus which is held together with interactions with pions also, gives you these connections. So I would say that if you're treating O4 and O6 independently, then there are some QCD effects that you're going to call beyond standard model physics if you're looking at a signal.
I see. So some of these operators have to be looked at in a correlated way.
Yes.
Thank you.
I will come back to it in a table. And I can write down also how exactly O4 and O6 are related, maybe in the exercise session too. And also that all of them are not equally important. In fact, almost all of them are tiny compared to the responses I will show you later. So the main point here is that you can map this. Of course, you can match the chiral EFT if you go back to the slide from yesterday. Of course, you can say, here's my chiral EFT scale. So I would be an energy scale somewhere here. For chiral EFT, this is a bit bigger here maybe. Chiral EFT scale is where Q are of the order m pi, which you need to describe nuclei. And you can also go to a lower scale where Q is much lower than m pi. And then you would have NR-EFT. And of course, just like we match the effective operators to chiral EFT, you can match the chiral EFT operators or the chiral EFT response to the NR-EFT response. But if you use NR-EFT only to analyze an experiment, then once there is a signal, I mean, at this point, there's no signal, so we don't have to worry about it. But once there is a signal, there are certain connections in these operators that come from pion exchanges, and you should include these directly. And it's not BSM physics. I hope that answered your question, Josef.
Yes, great. Thank you very much.
Okay, so let me turn this table here, which is just to show you this chiral counting, into a formula for the cross section and make it a little bit more explicit. Okay, so our main goal is to include all these QCD effects, and when I say QCD effects, I mean these chiral EFT aspects, the chiral physics, and we want to we have to truncate, and our guiding principle for truncating is to keep only operators that have some coherence that scale with A, because I will show you later there are many operators that are tiny because they are momentum suppressed and not coherent, so very, very unlikely. Okay, and if you do this, then a generic cross section can be written in this form. So this is the cross section here, differential cross section for Wimp nucleus scattering, where Q is the 3 momentum transfer. This is what we had labeled P before. So little q and little p is the same. V is, as you know, maybe I write it also, the relative Wimp velocity. And this other combination that appears here, this transverse velocity V T perp squared is the V squared minus Q squared divided by 4 times the reduced mass of the curly and the nucleus. Okay, so this is the relative velocity. This is the velocity of the Wimp with respect to the nucleus. Velocity of Wimp with respect to nucleus. And the reduced nucleus mass, mu reduced, is of course the mass of the, here it's big nucleus, mass of the Wimp, mass of the nucleus plus mass of the Wimp. Okay. Then there is are some different responses that get squared up. So there are some responses that can interfere. These C's are basically the coupling constants. So this is like the coupling, the constant for standard spin-independent interaction. And this corresponds to the response M. The M response is the spin-independent response. And the I is isospin, isoscalar, and isovector. So this is isoscalar and isovector. So where the response goes as n neutron number plus the number of protons, or neutron number minus the number of protons. And these CIs are then basically the product of Wilson coefficients, namely the operators in the BSM, the coefficients of operators in the BSM Lagrangian, times hadronic matrix elements, which correspond to the expectation values of the quark-gluon level operators in the hadron. Okay, and in these cases here, all of these C's, the CI's would carry I. Any C lower I is related to the nucleon, because only for the nucleon you have isoscalar and isovector. And for example, C pi up there is related to the pion. So Wimp describes the Wimp coupling to the pion. And the CB also has some relation. These combinations here depend on different pion-related things. Okay, so we have explained all these factors here. The overall factor, coupling times FR response function squared. In a particular channel. Okay, so so here is the M response, and that has coefficients Cm and Cm dot. The phi double prime response has the phi double prime coefficient, and there are some other coefficients that are related to other responses here, which have the same form as FIM. Okay, so the FM response here, F plus M response, is the standard spin independent response for which everybody likes to use the Helm form factor. Just that you're normalized. Okay, so this is the part for plus that scales as A. Okay, and you can see that these are fully coherent. Here you can also see that has the same FM, so the same scaling. And then there are different coefficients. Here's a first coefficient. Then this is the second coefficient is related to a radius correction, because the nucleon has a finite nucleon, so neutron and proton has a finite radius. So this part here is a radius correction, nucleon radius correction. Just like for if you measure the elastic electron scattering cross section, then the q squared part, the lowest part, is related to the radius of the nucleon. So this is a radius correction. Then all of these are spin independent. Then there is stuff that's related to the coupling of the pion. And then this one here is a semi-coherent response. This is a response that is almost like A, but a little bit smaller. And it's this phi double prime response. And this is related to that in a nucleus, you can also have shells with large occupation. So some large number of nucleons are in the same shell, and then this is coherent within that nuclear shell, not within the entire nucleus. And so we give it a fraction psi times A as scaling, where this psi is maybe something like 0.2 or so. Okay. And then similar to this momentum suppressed nucleon radius correction, there are other responses which depend on Q. So psi is just a function of Q and V perp, which have these labels 5, 8, 11. We will see later what they go like. Or maybe I can give one here, for example, psi 11. Psi 11 is just minus Q over 2 times the Wimp mass. Okay, so it's also Wimp momentum suppressed response, but not related to nucleon radius corrections, because those go as 1 over m nucleon squared, but over m Wimp mass squared. So it's a much smaller effect. Okay, so I hope this is not, this master formula is not throwing a big formula at you. So let me go through it slowly again. So what do you use for the so far spin independent? So maybe I should also color that in with purple. So so the standard spin independent corresponds to keeping only this with this, and I is equal to plus. Okay, then you can have isovector corrections. These you also know already. Then you can have of the standard response a nucleon radius correction. Then we learned that the Wimp can couple to the pion in chiral EFT. Then there are suppressed responses which are not fully coherent, but only coherent within a shell of the nucleus. And then there are further real momentum suppressed responses, and these I's 5, 8, 11 refer to the operators we just discussed, 5, 8, 11. So this is, as you can see, guided by putting in chiral EFT. So nucleons have a radius, pions exist, and things that are coherent. This scales as A squared, this scales as A squared momentum suppressed, and this scales a little bit momentum suppressed, but also suppressed by not full coherence, but only subcoherence. Okay, and now let me put all of this on like the master table. So now we organize things in terms of structure factor, and Fm is the usual Helmholtz factor for you, let's say. Structure factor Fm. Then there's the second one in here, the structure factor F pi, structure factor Fb, structure factor F double prime, and then just for comparison to normalize us, this is the spin dependent channel. So from here on, it's just spin dependent. So maybe this you don't want to look at in detail, but this is just to compare that you can understand the table based on what we discussed so far. And now you can see these are the possible QCD operators that you could have in a BSM type effective operators: Wimp's coupling to Q bar Q, Wimp's coupling to the trace anomaly, Wimp's coupling to other stuff, so many possible combinations. Then you can see for a given QCD operator, what if you take this operator and embed it into hadrons, what the chiral scaling would be. So scaling p squared, which is here constant, but order 1 or suppressed. So this refers to the big table I had before. And then we also do here the matching to this non-relativistic EFT operator. So up here are 01, 5, 8, 11. So you can see these are the 5, 8, 11 before. You can see here the overall scaling. So these really scale as A squared in the end. The response function scales as A, the cross-section A squared. And then you can see here some of them are suppressed both by Q and the transverse velocity. And then we also checked which of these is possibly interfering with the leading response 01. Okay, and you can see that here for these operators 5, 8, 11, there's always a no. So that's why in the master formula 5, 8, 11 is really momentum suppressed squared and doesn't, like the nucleon radius correction, interfere with FM itself, with the leading spin-independent response. The only response that interferes with the spin-independent one is this phi double prime response that's related to operator 03 and has this fractional coherence psi times A with these additional momentum response suppressions that are also in the previous formula. And there's a yes for it does interfere with 01. And also the pion stuff does interfere with 01. And you can see here the scaling with A. And there's a suppression here of the pion response. In front, this is related that that operator is Q cubed suppressed because it's a two-body current. Okay, and then just for comparison, the spin-independent case that we discussed yesterday does scale like single particle, order 1. It, of course, does not interfere with the spin-independent channel. And you can see here for the standard axial vector type coupling, where the Wimp couples to an axial vector quark, 04 and 06 combined. You would have to have independent BSM operator where you would have such a coupling here or some pseudo-scalar type couplings. Okay, so that's sort of the overall picture, and I would like to now show you a calculation of this cross-section looking at individual bits for Xenon 132. Any questions up to here?
I see no raised hands. No, Gaurav. Yeah.
Yeah, okay. It is related to the Wilson coefficient in your previous slide. So you assumed here that Wilson coefficient is, they don't depend on anything, but this is always a possibility that they could depend on, let's say, maybe the momentum here, which is mentioned. So if one wants to include,
be even further suppressed.
Okay, so they will be further suppressed. So okay, not that important. Okay.
Yes, we assume here that for us here we did we basically start from such a suppression which has constants, as you point out, Wilson coefficient, and we also do not study its electroweak running. So if that leads to some fine tuning or some additional things, then that's also not included. We assume at the level of embedding this in the hadrons, it's a constant. Any additional Q factors would only make things worse.
I see. But they could be important if it is like 1 over Q square dependence, right?
Yes.
Because Q is small, so they could be important. Okay.
Yes.
Thank you. Yeah.
Yes. Okay. And I think you could also in the running find some interesting regions of parameter space, of course. Okay, then let's look at a structure factor plot again. So this is taking the formula we just looked at and plotting now the individual responses for xenon 132. And the color scheme is roughly ordered according to its importance at low Q. So you can see the leading one here is the standard spin independent one, and this is indeed the one that's normalized to A squared, where A is 132, so it's a bit higher than 10 to the 4. Then the next important response is the black dashed line. That's the isovector, the n minus c squared for xenon, and that's smaller, but it has a very similar shape. Then the next two responses, so that's spin independent isoscalar and spin independent isovector. I think everybody's familiar with those. The next two lines here that survive at low Q are the purple and the orange lines, and they are both related to this chiral physics aspects. We decided to go for these two independent, that would be another lecture by itself, but we decided to go for these two independent, or another few slides by itself, two independent structure factors FB and FPi, and you have different combinations of these depending on whether you assume that you have a scalar, purely scalar coupling to the pion, or you couple through other operators to the pion. So they are both related to this two-body current effect, where you couple. So for example, FPi, if you have, let me highlight this maybe here, this one, for example, would be the response if you have a purely scalar coupling to pion. And if you have other combinations, you get other things for the pion. But you can see that these two-body, so that was what I wanted to draw, where here's my pion, here's my nucleon, and my current is to the pion like here. And so you can see these two-body current effects, FB and FPi, they are the next important effects. After that comes the green combination, solid and dash. These are isoscalar and isovector of q squared over 4m pi squared. So if you go back to the table here, then that's for example related to these operators here, where you have for m chi, for example, right? So if you square this, it's q squared over m chi squared q squared over m chi squared times the standard a squared. And so the green part here is related to O11. I also show you something about O3 later, but basically these first non-trivial operators from the NREFT are at least 4 orders, from 10 to the 4 down to 1, suppressed compared to all of this chiral physics here. Okay, so if we look at this in an actual calculation, we see that the dominant corrections to the usual spin-independent stuff are QCD effects, coupling to the pion, isovector corrections, and also some radius corrections. And the first new NREFT operators, O11, is this q squared over 4m chi squared, is 4 orders suppressed. And we go back, this phi double prime in the Fitzpatrick language is related to O3. And phi double prime can interfere with FM. So it's an basically this is not suppressed by phi double O3 squared. It's O3 mixes with O1. And so if we look at other operators here, not just the 11, which we can read off here directly, but if we look at other operators, then also the red line here, which is the mixing of O1, the standard Helm form factor, let's say, with O3, or it's not O3 squared, but mixed into O1, then O3 is also 10 to the 4 suppressed or so. And here's our O11, which we just discussed as well from the previous plot. Okay, so the only real operators here are relevant are O3 mixing into the standard response and O11. If you look at O8, or if you're interested in O5, which we even kept because we thought it could be interesting, then you can see that that's even more challenging than the inelastic scattering experiment. Okay, so with this, that sort of wraps up. Let me maybe stay in time here. Wraps up the general coherent spin-independent response, which is looked at in this master formula here, which includes the standard spin-independence path stuff and a number of QCD corrections that are all more important than the new operators 5, 8, and 11. And I want to stay in time so you can ask me more questions, but I basically want to give you a sort of quick advertisement of what we skipped. One is, now you can ask the question, since this is the same structure factor plot as a function of Q, but overlaid here is sort of the relevant Q region for xenon-like detector. This is the right region. This is from work together with Alex Wiegut from back then in Münster. And this is the xenon detection region here. And you can ask the question, well, is it actually possible for a xenon type experiment to distinguish whether the form factor decreases or whether you have a momentum suppressed response that would increase, or whether you have one of these two-body current F-pi responses. So can one discriminate these responses? And the answer is, with a large enough detector like Darwin, yes. So when one can really discriminate the shape of these responses, and then it really matters what type of QCD effects you put in. So I have 2 more slides. I could discuss that further. And then finally, I wanted to show you that if one takes the coupling to the pion only, so one assumes the Wimp coupling is in the slice of the only is such, we take the slice of BSM parameter space where the Wimp couples to the pion, so there's just this C pi response. And look at it, then we already discussed that that has a is more important than spin dependence. So I think I had that in my lecture yesterday already. So Wimp pion interactions are somewhere between standard spin independent and spin dependent, because it scales better than single particle like, but not as good as A squared. And Xenon 1 ton put the first limit on this Wimp pion coupling, which you can see here. And so with this, let me wrap up here and give you the outline here to remember the main points. So today we finish off spin-dependent scattering by looking at this very interesting inelastic scattering channel. Then we discussed, for the most part, a general coherent, meaning something that scales with A, or at least a fraction of A, Wimp nuclear scattering, and discussed its implications, that there's actually more, dark matter direct detection has more than just limits on single nucleon cross sections. And I want to again advertise that all our spin-dependent structure factor fits are in those 2 papers. This is the newer paper, but if you would want to compare to the limits reported by other experiments, you should use these fits, just to use exactly the same input. And then on our group website, which is stronginteractions.eu, on the left, there's a button called Chiral EFT for dark matter, which you can click on. And then you can download a Jupyter notebook, which calculates all these general coherent responses, which I had before for any nucleus that's detector relevant. Again, my email address in case of questions. And with this, let me just flash the summary, which is the same summary from last time, and finish here to not go too much over time. Thank you very much.